One type of small plane in common use today comes from the manufacturer with a note that says it can carry 2,600 pounds of passengers, but it doesn't say how many passengers that is. Deciding upon how many passengers equals 2,600 pounds is an airline decision. If the airline decides that its passengers will have weights that are normally distributed with a mean of 167.6 pounds, then they can put 2,600 divided by 167.6, or 36.99 passengers on this airplane. Let's just call that 37 passengers because it's close enough to 37. Well, imagine that today the crew chief notices, as the passengers are boarding, that they're all adult males. The crew chief mentions this observation to his pilot. The pilot, being an old guy and a statistics buff, shouts, "Glory, ASCII 0! That means the assumption of mean weight equals 167.6 pounds is incorrect." This pilot, let's call him Charles, knows that adult males have weights that are distributed normally with a mean of 182.9 pounds and a standard deviation that's equal to 40.8 pounds. Charles quickly grabs his slide rule and does a quick computation. Moments later, he puts down the slide rule and sighs. "Leaping lizards, we can't take off until some changes have been made." Now, what was it that Pilot Charles computed? Most likely, Pilot Charles computed W bar, but not for the mean of 167.6 that the airline had given him, but since he observed that these were all adult males, he probably used the more correct normal distribution of 182.9 pounds for the mean. Well, the sum of the weights, if that sum exceeds 2,600 pounds, then he's overloaded. Now, W bar, we know how to compute the average of a sample, would be the sum of the weights of all the passengers divided by how many passengers we have. So if we would then just take the number of passengers we have times W bar, then that would be equal to the sum of the weights. That's why Charles is interested in recomputing W bar, not for a theoretical value, but for the most likely value for the people that are getting on his airplane. Now, like Charles, let's compute W bar with assumptions that we're going to pick up from the observation that we've got adult males on the airplane and from the central limit theorem. You know this is important because it has the word central and the word theorem in it, and so it has to be an important result. And it tells us how to compute probabilities for averages. A random variable, W for example, the weight of an individual passenger, would have an average if we take a sample of size n passengers. And the central limit theorem says W bar is normally distributed with a mean, now this is W bar for adult males, and so the mean is 182.9, and the standard deviation is the population standard deviation, which is 40.8 pounds, but, and here's the important thing to remember, but divided by the square root of the sample size. And in this example, we have a sample of size 37. And so to calculate the standard deviation for W bar, we would take the 40.8 and divide by 37. Now that we're using the correct probability distribution, we need to calculate the probability that W bar exceeds 167.6 pounds, because if that's true, it puts us over the load limit for passengers. So I've used Minitab and calculated the probability that W bar, with the distribution immediately above in green, would exceed this value, and I found the number to be 0.9888. There's a 99% probability that my aircraft is overweight, is overloaded, and that's what we mean by some change is going to have to be made. You don't want to take off knowing that you're exceeding the design load of your aircraft. So, interesting, huh? Good thing that Pilot Charles likes statistics. Get back with you in the next video. Thank you.